Welcome back to the deep dive. Today, we're exploring a really fascinating collision point, the subtle, expressive art of musical performance meeting the absolute cutting edge of generative AI.
Right.
And the goal here isn't just to, generate some movement. It's to capture the sheer intricacy and, frankly, the emotional weight of a human playing an instrument.
It's a massive challenge. I mean, instrument performance isn't just choreography, is it? It's a physical conversation between the human body and this external vibrating object.
A conversation, that's a great way to put it.
Yeah, you have to reconstruct the complex, really delicate dynamics of that performer-instrument interaction, and you have to do it down to the millimeter.
And for this deep dive, the instrument chosen is a true test case for this kind of synthesis. We're talking about the cello.
The cello is, well, it's perfect for this. It demands this exquisite coordination. It has that massive pitch range, from rumbling bass all the way up to high soprano.
And crucially, the playing positions are continuous.
Exactly.
Yeah.
Unlike, say, a fretted guitar or a keyboard, there are no discrete fixed points. Every subtle shift in the left hand, every millimeter of bow position, it all impacts the sound, its motion generation taken to the absolute extreme.
It requires whole body, highly expressive control. So we're looking at a technology designed to tackle this exact challenge. It's called LGR. That's Expressive Cello Performance Motion Generation for Audio Rendition.
Right. LGR is a pioneering, really state-of-the-art framework. It's diffusion-based. And its whole job, its core mandate, is to generate whole-body, fine-grained performance motion.
Solely from audio.
Solely from audio.
Yeah.
And the novelty is that it's really committed to moving beyond just, simple limb modeling. It wants to capture the full complex choreography, including those critical nuanced interaction points with the instrument itself.
Okay, let's unpack that, starting with the input. If you're trying to generate this kind of performance, you generally have two choices, right? Symbolic representations like sheet music or MIDI or just raw audio.
That's right.
LGR went with raw audio, which at first glance seems counterintuitive. I mean, audio is continuous, it's unstructured. Why is that complexity actually an advantage here?
It's all about expression. I mean, think about it. Symbolic music, MIDI, it tells you what note to play. But the raw audio tells you how the note was played. The audio waveform, it sort of embeds richer, expressive power of performance. It captures the vibrato, the dynamic swell, the performer's unique interpretation, even subtle timing shifts like rubato.
So you want the movement to reflect the feeling of the performance, which is only present in the sound itself.
Exactly. If you condition your generation on MIDI,
Yeah.
every single time you generate that same piece, the movement will be pretty similar. But condition it on audio, and you can have different performances of the same piece, say a romantic one versus a very dramatic one, and they'll generate appropriately different nuanced movements.
And I guess from a practical standpoint, audio is just everywhere.
It's globally accessible.
Yeah.
Absolutely.
Okay, that makes the choice very clear. So let's get into the mechanics. How does LJ actually turn that raw audio into movement? You mentioned it's diffusion-based, using a denoising network built on something called DIT blocks. For someone who follows AI but maybe isn't a deep learning specialist, what does that architecture actually mean?
So think of a diffusion model like this. You start with pure static, just random noise, but for motion. And then you progressively, step by step, clean it up until it matches the performance style described by the audio input.
And the denoising network is what does the cleaning.
That's the thing doing the cleanup.
Okay, and the DIT blocks, what's that?
DIT stands for diffusion transformers. They basically replace the traditional convolutional neural networks, or CNNs, that you often see in image diffusion with a transformer decoder structure.
Okay, and transformers are great at handling sequence data.
Exactly what motion is, a sequence of poses over time. So by using them, the model can look at the whole sequence, predict where a specific joint should be at a certain time, and then correct the noise based on the context of what came before and what's coming next.
That gives it that temporal coherence. It makes the motion flow. But how does the audio actually, talk to the motion generator?
So the audio conditioning features are extracted by this huge, specialized, pre-trained model called Jukebox. And it's frozen, which just means its parameters aren't being trained during this process.
It's just listening.
It's just listening and providing these highly refined, expressive music embeddings. And then these embeddings get integrated into the denoising process using what are called cross-attention mechanisms.
Cross-attention.
It just means that at every step of that cleanup process, the motion model looks at the audio features to decide how to guide the motion, making sure the final movement matches the expression that Jukebox captured.
So jukebox is doing the deep musical listening, and cross-attention is the bridge that forces the body to move in sync with that emotional data. But as we said at the top, generating movement isn't enough. The movement has to obey physics.
Precisely. And this is where a lot of previous work kind of faltered. They could generate a human shape that moved, you know, generally correctly, but when you zoomed
The
in,
bow is floating an inch off the strings.
so the fingers are clipping right through them.
Yeah.
LGR solves this by introducing hard domain knowledge constraints through these custom losses, which they call the interactive contact loss, or ICL.
RACL. It sounds like the system's conscience, sort of enforcing physical reality. But before we get into the details, I have to ask, isn't adding two brand new custom loss functions like this incredibly complex to design and tune?
Oh, yes.
Are you sure the accuracy improvement is worth that engineering overhead? You're moving away from a general model to something hyper-specialized.
That is a really important question because, yes, specialized losses are complex, but in a high-stakes interactive domain like this one, general motion metrics just don't capture the physics. They can't. If the motion you generate is supposed to be usable in, say, animation or education, the bow cannot be 25 millimeters away from the string.
It's a non-starter.
It's a non-starter. The ICL is that necessary bridge between what's geometrically possible and what's required for actual physical sound production.
Fair enough. Okay, let's break down the two parts of ICL then.
So we have the hand interactive contact loss, or HICL, for the left hand. That's for pitch control.
Right.
And then the bow interactive contact loss, BICL, for the right hand, which is for sound excitation.
Okay, tell us about HICL for the left hand.
So HICL enforces two really specific crucial constraints. The first one is that the note-playing finger must maintain firm contact with the string. If the audio says a note is being played, that finger better be pressed down, unless, of course, it's an open string.
And the second constraint.
This one is more subtle. All the other fingers must avoid contact with the position being pressed by the note-playing finger.
Yeah.
They have to hover naturally without messing up the pitch.
So it prevents visual artifacts and makes the fingering look plausible.
Musically plausible, exactly.
And then there's BICL for the bow, the engine of the sound.
The BICL is maybe even more demanding. It enforces that the bow has to maintain contact to vibrate the string, and it has to move perpendicular to it. The audio stream identifies the what they call the activating string, so which string is currently supposed to be vibrating.
And BICL uses that information as a constraint.
As a hard constraint, yeah.
Yeah.
It ensures the bow not only touches the correct string, but also maintains these very precise geometric relationships between its two ends, the frog and the tip, relative to that string.
The level of detail here is just incredible. But let's go back to your point about the trade-off. What measurable proof do we have that this complex ICL system is actually delivering?
We can look right at the ablation results, specifically for the bowstring distance metric, or BSD. It measures the deviation between the bow hairs and the target string. The model that was trained without the ICL system,
Yeah?
it resulted in a BSD of 25.2 millimeters.
Wow. Okay. That's a huge margin of error. That's an inch. It looked completely broken in any rendering.
It's an inch of air between the bow and the string. It's unplayable. But the model trained with both HICL and BICL, it drastically reduced that error to just 5.40 millimeters.
That is a massive difference.
It's a five-fold quantitative improvement just from integrating these domain-specific physics-informed constraints. It proves that the engineering complexity was absolutely necessary to cross that threshold from just general movement into believable, realistic performance.
That staggering leap in physical accuracy, that's what defines this work. Okay, let's transition now to the data side, because these powerful models are useless without clean data, and it sounds like existing data sets had some big problems.
They absolutely did. Existing data sets, like the original SPD, they usually just provided raw, disconnected key points. There was no kinematic information, no positional constraints.
You can't train a system to understand physics if the training data doesn't give you the full physical picture.
You got it. So ELGAR used this new data set, SPD-GEN, which they put together from 81 cello performance pieces.
And what specialized cleanup did they apply to the human motion data?
Okay, so first, they had to standardize the performer's body. They used a process called human normalization, which involved a two-stage inverse kinematics process, or IK, using the SMPLX format.
Okay, we've had a few bits of jargon there. For our listeners, what is the SMPLX format, and why is standardizing the virtual body so crucial?
So SMPLX is a standard statistical body model. It represents the human body as a mesh that you can manipulate with simple parameters for pose, shape, and expression.
So you're fitting everyone's movements onto one average digital body.
Exactly. It makes the motion itself universal and reusable, no matter what the original performer's size was.
And inverse kinematics.
IK is basically reverse engineering. If you only know where the hand is in space, IK helps you calculate what all the joints up the chain, the wrist, the elbow, the shoulder must be doing to get it there. And the two-stage process they used really prioritized getting the wrist fitting right, which is paramount for bow control.
Got it. Now, the final motion data is represented by 309 dimensions, mainly using 6D rotations for joints instead of simple 3D coordinates. Why is rotational data better?
Because the human body is a kinematic chain, right? It's governed by joints, and joints operate on rotations and limits, not just free movement in space. If you use simple XYZ coordinates, you might accidentally generate a motion where a knee bends backward or an elbow spins 360 degrees.
A physical impossibility.
Total impossibility. 60 rotations intrinsically encode the structure and limits of the human skeleton, which makes the synthesized movements instantly more plausible.
That makes perfect sense. And that brings us to the great aha moment with the instrument itself, the ceLlo normalization. This involved fixing a structural error in the original data?
Yes. This is one of those details that just shows how much domain expertise was involved. They found that in the original SPD motion data, the cello bridge was modeled as being completely flat.
But any cellist knows a real cello bridge is arched.
It's arched. And that shape change is essential for simulation.
Why? What does that do?
Because if the bridge is flat, the bow can't play the two middle strings, the A and the D strings, without also hitting the strings next to them.
Ah, so you get clipping.
You get a serious visual artifact, yeah. The bow clips right through the string it shouldn't be touching. So even with perfect motion data, if the geometry of the instrument is wrong, the whole simulation just breaks down.
So by restoring the proper arched bridge, they ensured that HICL and BICL could even work correctly in the first place.
Precisely. It's a perfect example of how the physical world has to constrain the digital model.
Okay, so we have the specialized data, the robust architecture, the physics-informed losses. But then once LGR was working, they realized standard evaluation metrics weren't going to cut it either. What was the problem with something like FID?
Well, traditional metrics like Frechet inception distance, FID, they're distribution metrics. They measure how closely the generated data distribution matches the real data distribution.
Right.
But when you impose hard constraints like HICL and BICL, you are fundamentally altering the distribution. You're throwing out all the physically unrealistic samples.
So the synthesized data should be different from the raw, noisy data.
It should diverge slightly, which makes a standard FID score potentially unreliable. Plus, the data set is relatively small, which also complicates things.
So they needed metrics that directly tested the interactive realism. What were they?
They introduced several. The first two we've actually already talked about. Bowstring distance, BSD, measuring the bow's accuracy, and finger contact distance, FCD, which measures how accurate the note-playing finger is. Shorter distances mean higher musical accuracy.
And how did they actually measure the musicality?
For that, they used a bowing F1 score and cosine similarity. This basically assesses if the generated bowing attacks, when the bow changes direction, align with musically suitable rhythm and phrasing. It's a holistic assessment of timing, physical interaction, and musical intent.
It's clear that the success of LGR is really measured by how well it models that relationship between the performer and the instrument. The applications seem obvious: animation, education, interactive art.
Huge potential.
But let's look at the limitations the researchers themselves acknowledge, because that's often the most insightful part of any research.
Certainly. They noted three main limitations. The first is context. LAGR has limited long-term context awareness. For quick passages, it's great. But during very long sustained notes, the model can sometimes generate an unnatural or abrupt bow transition because it sort of loses track of the larger musical phrase.
It needs better long-range sequence modeling. What about the actual pressure applied to the strings?
Right, that's the second limitation, pressure. The model simplifies finger string pressure into a binary state. It's either pressed or it's not pressed.
But a real cellist uses varying force.
Of course, and that changes the tone quality. Modeling that finer pressure would require integrating other data, like from force sensors, which just isn't in the motion capture data right now.
And finally, there's the complexity of actually using this motion in a professional pipeline, like a CGI movie.
And that's the critical challenge they call retargeting complexity. The generated motion, which is in that SMPLX format, has to be retargeted or transferred onto a completely different virtual character, One that's taller, shorter, has different proportions.
I would have assumed commercial animation tools handle that pretty easily.
They handle the general movement, sure, but they often completely neglect the interactive constraints. When you change the character's bone lengths, the distance between the hand, the bow, and the cello all changes. And the retargeting process typically throws out that critical, fine-grained interaction.
The very thing that dropped the bowstring distance to 5.4 millimeters.
Exactly. So the animator has to go back in and manually fix every single frame where the new character's hand is now clipping or floating. It just neutralizes the AI's precision.
Wow. So the fine-grained interaction is lost, and it turns a successful AI generation into a costly manual fix.
It does. It's a huge unsolved problem that plagues the transition from academic motion synthesis to real industry application.
So does that mean the engineering cost of ACL and the arched bridge is wasted if we can't reliably transfer the output?
I wouldn't say wasted. It frames the next research question. We've proven we can synthesize the interaction. The challenge now is to create retargeting methods that are constraint-aware methods that automatically adjust the character's pose to preserve that 5.40 millimeter distance, no matter the character's anatomy.
Okay, let's bring this deep dive to a close then. LDR is a pioneering system for whole-body cello performance, achieving this incredible physical fidelity by using diffusion models conditioned on expressive audio and, crucially, incorporating vital domain knowledge.
Things like the hand and bow interactive contact losses. The ability to generate motion that actually respects the physics of sound production, enforced by those custom metrics like FCD and BSD, that's a huge milestone.
So if AI systems can now accurately synthesize this incredibly precise, detailed physical interaction between a performer and an instrument, down to the geometry of an arched bridge and millimeter-level contact, then the next great unsolved problem in digital animation is shifting.
It is. We've gotten really good at generating realistic motion. The new frontier is mastering the reliable, automated preservation of that intricate, synthesized interaction when the motion is applied to any other digital body.
It forces us to think not just about the digital body, but about the invisible forces, the physical constraints, and the relationships that connect that body to the world around it. How do you digitize and transfer the performance relationship?
That's the question.
And that's the question pushing the boundaries of future animation and interactive graphics research. It's definitely something to keep in mind the next time you see a complex piece of digital choreography.
Always more to learn.
Thanks for diving deep with us. We'll see you next time.